We are in Chapter 6, Applications of Integration. Section 6.1 is Areas Between Curves. In Chapter 5, back in Calc 1, we defined and calculated areas under the graph of a function. We now will extend upon this idea to find the area between the graphs of two functions. So in the pictures right below this, you can see two curves sketched there. We have it called y equals f of x and y equals g of x. So the top function again would be our f of x function and the bottom would be our g of x. And to find that area in between them, we're going to divide that area into rectangular regions. So dividing this into rectangular regions, I'm going to go ahead and look at just that third rectangle that we have there. And that width that we have for that rectangle is going to be called our delta x. And you'll see that we are finding the height of that rectangle by using the midpoint method. So I'm going to go ahead and call that value right here that we are at is xi star. This is our third one though, but I'll just say in general it will be xi star. And then to find the height of this third rectangle here, it would have to be the top function minus that bottom function evaluated at x of I star. So it'd have to be f of x of I star minus g of x of I star. So to calculate the area between the two curves, f and g, and between the vertical lines a and b, where f and g are continuous functions, and also f of x is greater than or equal to g of x for all of our x in that closed interval from a to b. If we divide the area into n strips of equal width and then approximate the ith strip by a rectangle with base delta x and a height of f of x of I star minus g sub x I star, the approximation appears to get better and better as n increases, so as n approaches infinity. So the area of the region is defined as the limiting value of the sum of the areas of these approximating rectangles, like what we saw back in Calculus 1. The limit of the sum can be defined as a definite integral. So there's going to be three cases that we're going to be looking at in regards to finding the area between two curves. The first case says the area A of the region bounded by the curves y equals f of x and y equals g of x, and the lines x equals a and x equals b, where f and g are continuous and f is greater than or equal to g for all x in that closed region a to b, is going to be defined. And I'm going to go ahead and sketch a curve. A lot of us are a little bit more visual, and it's nice to have a visual representation of these graphs. So it does say that they're both continuous functions and that we're going to be defining this between, we'll say, a and b. So I'm going to go ahead and just draw a random curve here, and I'm going to call it f. And f of x is greater than or equal to g of x. So I'm going to go ahead and draw another graph over here. Just say g is going to be lower than it. And I'm going to call this one g of x. And so between a, which is right here, and b, which is right here, we are trying to find that area between those two curves. So to find the total area between f of x and g of x, we're going to be looking at that limit as n approaches infinity of the sum of all these rectangles that we would have. So for example, we would say that first rectangle right in here we would have, but again, as we discussed up above, this approximation is going to be more accurate if we have an infinite amount of rectangles. And so we're going to be using a definite integral. And so to calculate that area, and call a, which is going to be between a and b. And again, talking about each of those rectangles, the height was f of x minus g of x. And then that width width was delta x, which for us we're going to call dx. And this is how we would calculate that total area between F and G, between A and B. So a little note here, you always do your top function minus your bottom function whenever you have this kind of setup. And again, this is our first case that we have. So the example right below this says, sketch the region enclosed by the given curves. Decide whether to integrate with respect to x or y. Draw a typical approximating rectangle and label the height and the width. Then find the area of the region. So at this point, we've only talked about integrating with respect to x, which is why we have a dx here. But we will get into case 2 where we integrate with respect to y soon. So for right now, we're going to go ahead and sketch the two curves that we have. The first one is y equals x squared minus 4x, and the second one is y equals 2x. So first one is going to be a parabola, and the second one is going to be a straight line. For this example, you will notice that it does say enclosed by the given curves, and again, that first curve is a parabola and the second curve is a straight line. Since it does not tell us those values of a and b that we would have to integrate between, we have to figure those out on our own. And so since it's enclosed by, that's going to be where those two graphs are going to intersect. And so I'm going to go ahead and set these two equations equal to each other. So we have x squared minus 4x would be equal to 2x, and that would be where they would intersect, and that would be that enclosed region. Solving this, I'm going to subtract the 2x. And then I can factor out an x. And then I get a value of 0 and 6. So these are the two values that I know that I need to be integrating between. So for this example, we also need to sketch and draw an approximating rectangle and also the region. So sketching this, I know that my values of x are going between 0 and 6. And then my values for my y, I know definitely are going to go all the way up to at least 12. And then we'll go down to -4 or -5. And then to graph that second equation, that one is really nice. It's just a straight line. And I know that if I substitute in 0, I get 0. And substituting in 6, I get 12. And so that's the graph of the second equation that we have, y equals 2x. The first one is a parabola, and so just putting some of these values on, I know that at 0 it's also 0, and at 2 we would end up with -4, and then at 4 we end up at 0, and then at 6 we end up at 12. So going ahead and sketching in the parabola here, I can see that this is going to be the region that we need to find the area of. So I also need to draw in an approximating rectangle. So anywhere on this graph, and again, remember it's going to go from our first function, which is going to be y equals 2x, down to our second function, which is going to be y equals x squared minus 4x. And so our rectangle here, if you draw in the rectangle, which has a width of delta x and a height of our top function minus our bottom function, we can calculate our area, which is going to be the integral from a to b. And our a value here is 0 and our b value is 6. So from 0 to 6 of our top function, and for this one it is 2x, minus our bottom function, which is x squared minus 4x. And we are integrating with respect to x. This has a delta x down here, so we know that we are dealing with integrating with respect to x. So I'm going to go ahead and put a dx back here. From here I can simplify the function by distributing the negative and then combining my like terms, and then we can integrate this. So from here we end up with 2x plus 4x, which would be 6x, minus x squared dx, which is a nice function to integrate using the power rule. So going ahead and integrating this, we get 3x squared minus 1/3 x cubed. And then we have to evaluate this using the fundamental theorem of calculus from 0 to 6. So substituting in 6, and then substituting 0 would just be 0 for this, we get a total area of 36. On the next page, we have another example that says sketch the region enclosed by the given curves and find the area. So for the first one on here, we have a parabola and another parabola. So we're going to go ahead and sketch this. And again, it does say enclosed. So in order to do this, we need to set these equal to each other. So we have x squared is equal to 4x minus x squared. And we're going to move everything over to one side and then solve this. So we get 2x squared minus 4x would be equal to 0. Factoring out a 2 and an x, we get x minus 2 equals 0. So our values are going to be at 0 and at 2, where this equation would be equal to 0. And so this again is our a value and our b value. So this time I know that when I sketch my curve, I am going to be looking at the values between 0 and 2. And then I also realized that these values, if you look at the first graph, it looks like the highest that we would go on our y-axis would be 4. So graphing our first parabola, it's y equals x squared. So 0 would be at 0, 1 would be at 1, 2 squared is 4. And then graphing our second parabola, this is going to be 4x minus x squared. So substituting 0, it's at 0. When we substitute in 1, we get 4 minus 1, which is 3. And then substituting in 2, we also arrive at 4. And so our second parabola, which opens downwards, is actually our top one. So this is y equals 4x minus x squared. And the first one that we graphed is our bottom function, y equals x squared. So again, we're looking for this region that is enclosed by these two curves. And drawing our approximating rectangle on here. You can again see that that width would have a delta x, so we are integrating with respect to x. And so our area here is going to be equal to the integral from, again, a and b are 0 and 2. And then we have our top function, which is 4x minus x squared, minus our bottom function, which is just an x squared. And again, since we are integrating with respect to x, we're going to put a dx. We can combine our like terms and simplify this. So we have from 0 to 2 is our integral. And we end up with 4x minus 2x squared. And then dx. And then integrating this, we arrive at 2x squared minus 2/3 x cubed. And then we're going to evaluate this from x equals 0 to 2 using our fundamental theorem of calculus. Substituting in 2, we get 2 times 2 squared minus 2/3 times 2 cubed. Substituting in 0, we just get 0 for the whole expression. Working this out, we get 8/3. There is a second part to this example, part B, that we're going to circle, and we're going to work on this one in class together. And then we get down to case 2, which is on the top of page 3. Case 2 says the area between two curves y equals f of x and y equals g of x, and the lines A and B, where f and g are continuous, and f of x is greater than or equal to g of x for some of the values, not all of them, but for some of the x in that closed interval from A to B. And then g of x is greater than or equal to f of x for other values in that interval from A to B. So what happens here is those graphs are going to cross, they intersect somewhere between that interval from A to B, and they switch from one being greater than the other. So again, we're going to go ahead and sketch a curve here. And again, we'll say this goes from A to B. And I'm going to go ahead and draw f of x first. And we'll say here's f of x. And then I'll switch colors. And I'm going to sketch on g of x, which you'll notice they intersect. So I'm going to go ahead and call this one g of x, f of x. And they switch at this point right here from which function is above the other function. So I'm going to call that point right here, point C. So you'll notice that there's actually two different areas that we have. So this first area here, and we'll call this one A1. So the area for the first one is going to be the integral from A to C of, and then our top function for this case is f of x minus g of x, which is our bottom function. And again, integrating with respect to x, if you were to draw on that approximating rectangle, you would see that that width is a delta x. And then we're going to talk about that second area that we have, which is over here. And we're going to go ahead and call this area A2. So A2 is going to be the integral. So our starting value would be from C to B. And this time our top function is actually g of x. So g of x minus the bottom function, which is f of x, and then dx. Again, if you were to draw on those approximating rectangles, we would see that that width of that rectangle is a delta x, or dx, as we integrate. So to find that total area that we would have between x equals a and x equals b, so our total area we would find by adding together a1 plus a2. So there's an example right below that says sketch the region enclosed by the given curves and find the area. So for this one, we are given two functions, and then we're also given values of x. So first thing I'm going to do is I'm going to go ahead and sketch this. I do know that the values that we have are going to be between 0 and pi. So I'll go ahead and put pi out here. Between those would be pi over 2. So graphing my first function, it's y equals cosine of x. Y equals cosine of x is going to go ahead and start at 1 when cosine is 0. And at pi over 2 we get cosine of pi over 2 is 0. And at pi we get cosine of pi is negative 1. And so going ahead and sketching in that cosine curve, this is going to be y equals cosine of x. For my second graph, I'm going to go ahead and switch colors here. I have y equals 1 minus cosine x. So cosine of 0 is 1. 1 minus 1 would be 0. So starting there, at cosine of pi over 2, we have 0, and 1 minus 0 would be 1. And then dealing with cosine of pi, we get -1. So 1 minus -1 would actually give us 2. So going ahead and sketching this curve on also. This is going to be y equals 1 minus cosine of x. So I notice on here that these two curves are going to intersect. And they intersect at a point looks like a little bit smaller than pi over 2. So to determine exactly what that value is, we're going to go ahead and set these two curves equal to each other. So we have cosine of x is equal to 1 minus cosine of x. To figure out the value where those two curves intersect. So solving this, I'm going to go ahead and move my cosine over to the other side. So I have 2 cosine of x equals 1, or cosine of x is equal to 1/2. Again, remember we are in between the values of 0 and pi, so we're going to be only dealing with those first two quadrants when you think about the unit circle. And so thinking about where cosine of x would equal 1/2, we get a value of x equals pi over 3, which makes sense thinking about our graph up here. So this would be the value of pi over 3. So to do this, we need to find area 1, which we'll call A1, and area 2, which we'll call A2, which again, we now have to integrate from 0 to pi over 3 to find the area of A1, and then from pi over 3 to pi to find that area of A2. So let's go ahead and find the area of A1 first. So to integrate this, we're going to integrate from 0 to pi over 3. And then our top function, which for this problem is going to be cosine of x, minus our bottom function, which is going to be 1 minus cosine of x. And then we are integrating with respect to x, so dx. So from here we are able to combine our like terms. So again, integrating from pi over 3, from 0 to pi over 3, and we get cosine minus negative cosine is going to become 2 cosine of x minus 1 dx. So then integrating this, we have 2 sine x minus, integrating 1's just x, and then we're going to evaluate this from x equals 0 to pi over 3. So substituting in pi over 3 first and then 0 next, we get 2 sine of pi over 3 minus pi over 3 minus, and then substituting in 0, we have 2 times sine of 0, which is just 0, minus 0, so that whole thing would just be equal to 0 there. And then thinking of your unit circle, sine of pi over 3 is equal to rad 3 over 2 minus pi over 3. And so this simplifies to rad 3 minus pi over 3. This is not my answer. This is just one of the areas of that first region that we have, which was between 0 and pi over 3. We still need to find area of our second region, which we call A2. And so to set up our integral for A2, we are going to be integrating from pi over 3 to pi. And we're going to do our top function minus our bottom function. Top function this time being 1 minus cosine of x minus our second function, which is cosine of x. Still integrating with respect to x, so dx. Combining our like terms to integrate this a little bit nicer, we get pi over 3 to pi of 1 minus 2 cosine of x dx, which we integrate just like how we did up above. Integral of 1 would be x minus 2 times the integral of cosine is going to be sine of x. Evaluated this whole thing from x equals pi over 3 to pi. So substituting in pi first, we have pi minus 2 sine of pi minus, and then substituting in pi over 3, we get pi over 3 minus 2 times sine of pi over 3. And so evaluating this, we have pi minus 2 times 0 minus pi over 3 minus 2 times, and then sine of pi over 3 is rad 3 over 2 like we saw up above. And from here, we have pi minus pi over 3, which is going to be 2/3 pi. And then we have minus negative rad 3 or plus rad 3. And so this is that area that we have for A2. So to find our total area, we need to add together A1 plus A2. And I have underlined both of these areas, so our total area is going to be rad 3 minus pi over 3 plus 2/3 pi plus rad 3. So combining our like terms, we have 2 rad 3's, and then plus pi over 3, and that's negative, plus 2 pi over 3 is going to be plus pi over 3. So our total area is 2 rad 3 plus pi over 3. And for these problems, you are always going to leave your answers in terms of radicals and pi's unless otherwise stated to round so many decimal places. And that usually doesn't happen until we get into the application part of this chapter. So case 3 says the area of the region bounded by the curves when x is a function of y. So we have x is equal to f of y and x is equal to g of y. And the lines y equals c and y equals d, where f and g are continuous, and f of y is greater than or equal to g of y for all y in that interval from c to d. So again, we're going to go ahead and sketch a graph of what this would look like. And this time, since our functions are in terms of y, our functions are going to be drawn a little bit different. So we're going to have f of y is going to be greater than or equal to g of y, and we're bounded by the values c and d. So I'm going to go ahead and put c on here, y equals c and y equals d up above. And I'm going to go ahead and draw my function y. This is f of y. And I'm going to go ahead and draw my g of y also. We'll say g of y. And so we're trying to find that area between c and d, which would be this area region in here. And so this time, if you notice, if you were to draw your approximating rectangles, drawing them vertically does not make any sense since my functions are drawn vertically also. So I'm going to go ahead and draw my approximating rectangle horizontally. And when I do, you'll notice that we have not a delta x, it's a change in y here, it's a delta y. And so since we have a delta y, we are going to be integrating this with respect to y. So to find our area here, we're going to integrate from c to d, lower bound to upper bound, and then we're going to do our larger function minus our smaller function. Larger function is that one on the right. So we have f of y minus g of y. And we're going to be integrating this not with respect to x, but because we have that delta y, so integrating this with respect to y. And so they'll note here, we're always going to do that right-sided function, the one that's on the right to the larger function minus the one on the left. So for the next example, it says sketch the region enclosed by the given curves and find the area. I'm also going to be drawing in that approximating rectangle so we can kind of see how that works. First thing I notice is that one of the functions is written in terms of y and the other one is written in terms of x. I also notice that I have a y equals 0 that's given to me. So I need to first graph these functions. You can graph them any way that you feel comfortable with. Graphing that first equation that we have right here, x equals y to the 4th. This is the same thing as y equals the fourth root of x. And then that second function is y equals the square root of 2 minus x. So trying to figure out what values I need to use in order to graph this, I need to figure out where it's enclosed. I do know y is equal to 0, so I will keep that in mind too. But to figure out where it's enclosed, I need to set those two equations equal to each other. So I'm going to go ahead and, since this way I rewrote the first equation is written in terms of x, I have y equals the fourth root of x. I'm going to go ahead and set that equal to the second function. So I have the fourth root of x is equal to the square root of 2 minus x. And so I'm going to go ahead and raise everything to the fourth power. And when I do, this is just going to be x. And then raising the square root to a fourth power, I would have an exponent now of 2. And so 2 minus x squared, I can FOIL or multiply that out, and I get 4 minus 4x plus x squared. Moving everything to one side, I end up with x squared. Subtracting x, I get minus 5x plus 4 would be equal to 0. Factoring this, we get x minus 4 and x minus 1 is equal to 0. And so we get a value of x equals 4 and x equals 1. So from here, looking at these values, you might notice that there's a little bit of an issue. The issue lies in that second equation that we were given, y equals the square root of 2 minus x, and you might not realize it until you go to graph the functions. But you'll notice that 4 is actually not in the domain. So if you were to substitute in 4, you would have 2 minus 4, which is negative 2. We don't deal with imaginary numbers for this. So I'm going to go ahead and I'll cross this one off, and I'll say that 4 is not in domain of our second function, which was going to be y equals the square root of 2 minus x. So keep that in mind. So right now I see that they're going to intersect at one value at x equals 1. So I'm kind of a little bothered by this from the last examples that we had. However, I'm going to go ahead and sketch these, and hopefully once I sketch it I have a little bit more insight to how to set this integral up. So I know that my value here just goes out to x equals 1, possibly, but I do need to figure out where they intersect. So I will put an x equals 1 on here, but I do know that's where they intersect. But graphing this, the first one that we have is y equals the fourth root of x. And so if x is 0, it would be 0 here. And then substituting in 1, the fourth root of 1 is just 1. And then going on, if I were to do the fourth root of 2, I can calculate that with my calculator, get a value. But it is a radical, so it is going off towards the right. The second equation that we have is y equals the square root of 2 minus x. And going ahead and graphing that, I notice that if I substitute in 2, I get a value of 0. If I substitute in 1 for x, I get a value of 1. And then so on as that goes, it did reflect with that negative x in there. So I'm going to go ahead and label these. The first one that I graphed was y equals the fourth root of x, or written as x equals y to the fourth. And then the second one that I graphed was y equals the square root of 2 minus x. You can definitely use any kind of shifting methods also that were discussed in pre-calculus to sketch your curves too. So here's my graph that I have. I also noticed that I have a y equals 0 here, so I actually had a third equation, and so y equals 0 is the horizontal line down here along the x-axis. So this would be y equals 0 is down here. And so I need to find this region enclosed by all three curves, which is going to be this shaded area that we have here. And so if you notice when you draw your approximating rectangle, You could set this up with two different areas to deal with it if you wanted to integrate with respect to x. If you were to think about drawing a vertical rectangle, you would split it at 1 and do the top function minus the bottom function and find those each and then combine them together. So we can always do that for some extra practice to see if you get the same answer, which you should. But I'm going to go ahead and try to integrate this with respect to y, because I notice that my two functions, I have a left side and a right-sided function. And so if I had an approximating rectangle here, this would be a delta y. I could be integrating with respect to y. My y values then that I'm going to be integrating from would be going from 0 all the way up to where they intersect, which was at 1. Since we are integrating with respect to y, I need to make sure that both of my functions are written in terms of y. So I have the first function that we were given is x equals y to the fourth, which is perfect. But that second function that we have is a square root of 2 minus x is equal to y. And this is in terms of x, and I need it to be in terms of y. So I can do that and just square both sides. I get y squared and equals 2 minus x. Then I would subtract 2, divide by a negative, and I end up with x equals 2 minus y squared. And so I need to make sure that both of my functions are written in terms of y. So to calculate our area, we're going to be integrating from 0 to 1. And again, this is in terms of y, so we will have that delta y, that dy, in my integral. And my right function, which my right function in my picture is y equals the square root of 2 minus x, which we just rewrote in terms of y, which is going to be 2 minus y squared minus, and then my second function that we have, the one on the left, is going to be the fourth root of x, or in terms of y, we would have y to the fourth. And then again, dy, since we are integrating with that respect to y. It's not much you can combine here. I will write it a little bit nicer though. We do have 2 minus y squared minus y to the fourth dy. Integrating this, we get 2y minus 1/3 y cubed minus 1/5 y to the fifth. And then we're going to evaluate this from y equals 0 to 1. And so we get 2 times 1 minus 1/3 times 1 cubed minus 1/5 times 1 to the fifth. Substituting 0, you just get 0. Working this out, we get 2 minus 1/3 minus 1/5, which is going to arrive at an area of 22 over 15. So think about, for this problem, how you could set it up and integrate it with respect to x instead of with respect to y and arrive at the same answer.